VisCoDeR is a tool that illustrates how comparative visualization can help to learn and use DR algorithms. The tool has two modes, the Discover mode and the Explore mode. In the Discover mode, you can qualitatively compare the results of different DR algorithms side by side. We provide various artificial and realistic datasets to try this out. While you also could upload your own data, we now select one of the default datasets that we added. Let us for instance pick the artificial Swiss roll dataset. The upper left corner offers different direct visualization of the three-dimensional data. Let us for instance select the 3D view, which shows the well-known pattern of the Swiss roll. The other 5 views show how different DR algorithms reduce this data to 2D. See for instance how these purple points end up in different positions in the different DR projections. The histograms on the right show the distribution of the data along each dimension. The gray value range shows the distribution of the original values on the respective axis. When hovering a point, a colored overlay shows the distribution of the respective class. When you click on one of the histograms, each DR scatterplot shows how that dimension is distributed along this projection. Let us click on the Y dimension. In IsoMap, we see that the Y values of the yellow dots are low, while the Y values of the orange dots are rather high, indicated by the white background. There are many other features, such as different setting options and tools for the respective algorithms, or the Show Proximity option. The Show Proximity option adds voronoi shading to the DR projections. Neighbors in the original high-dimensional space are shown in white. The PCA projection, for instance, reveals many false neighbors indicated by the white cells that are far away from the point that we hover here. IsoMap does a better job in retaining the local neighborhoods. For DR novices, we integrated an interactive text that explains the algorithms and ties them closely in with the interactive visualization. For example, to see how t-SNE works, you can try different examples, such as learning about which songs are played live in the Spotify song dataset. As soon as you move your cursor over the eye, you see in the t-SNE algorithm a circle in which the songs have a particularly high liveness. The other main mode of VisCoDeR is the Explore mode. Here you can see different DR algorithm behaviors at a glance by presenting hundreds of DR results directly in a metaplot. The metaplot is linked to an interactive color legend that encodes the different DR algorithms and their parameterizations. For example, if we hover over the IsoMap area, we can see that its cyan-colored projections mainly in the upper right corner of the metaplot. By clicking a point, you will see detailed results on the right. The brush function allows you to select specific areas in the metaplot and see which parameters lead to these results in the color legend. If we now select the following range of t-SNE projections, we can see that they were produced by a perplexity of about 35 to 47 and an epsilon that spans the entire bandwidth. It also works the other way around. In the color space, you can brush different epsilon or perplexity values of t-SNE. The respective selection is highlighted in the metaplot. It is interesting to observe that altering perplexity in the iris dataset is more sensitive than altering epsilon. The dots with the same epsilon are all over the place. In contrast, the dots with the same perplexity are close to each other, moving from the lower right corner to the upper left. When changing the dataset to MNIST, the aforementioned stability is no longer to be found to the same extent. As we can see, the results are almost equally dispersed when changing both parameters. Let's come back to the iris dataset, which consists of 2 well-separated blobs of points. This leads to an interesting behavior for different parameterizations of IsoMap. We can see that IsoMap's neighborhood graphs do not connect if the parametering is too low. Only with correspondingly high parameterization does the IsoMap deliver a usable result which is quite similar to the green MDS. On the other hand, The isomap algorithm seeks to provide more stable results of the MNIST dataset with one exception. However, this one exception results from the same problem as in the previous example. Due to two small neighborhoods, no useful result is delivered here. VisCoDeR is available online and free to use. More details can be found in our paper.